Hello everyone, I welcome you all to the course Unmanned Aerial Vehicle, and in today's lecture we'll see about Introduction to Rotary-Wing Unmanned Aerial Vehicles and Aerodynamics of Single Rotor. Introduction to Rotary-Wing Unmanned Aerial Vehicles. Rotary-Wing Unmanned Aerial Vehicle uses rotating wings to provide lift, propulsion and control. The key capability of this unmanned aerial vehicle is their primary distinction from fixed wing unmanned aerial vehicles is the ability to perform vertical takeoff and landing and maintain a stationary hover. These vehicles are ideal for missions in restricted environments, shipboard operations, and precise surveillance where landing space is very limited. This is an example of rotary wing unmanned aerial vehicle, Yamaha RMAX unmanned helicopter. Single main rotor, the conventional penny farthing layout with one lifting rotor and a tail rotor. The most conventional configuration featuring one large lifting rotor and a smaller side thrusting tail rotor to counteract the torque. This is an example of single main rotor aircraft. Here it is a single main rotor. You can see there is a single main rotor, and this is a tail rotor which is to balance the torque which is being created because of this rotating wings. Normally, if you see in this figure, the blade rotation is in this direction and the torque is in this direction, which is in the opposite direction. Torque will be always in the opposite direction of the blade rotation. So, this will push the unmanned aerial vehicle in this direction. So, to counter this direction, there is a tail rotor here, mounted the tail rotor, which moves the rotor in the opposite direction of the torque. So, in this way, it is been balanced. It stays at one place. Coaxial rotors. It features two rotors mounted on a single mast rotating in opposite directions to balance torque, offering high hover efficiency and compact dimensions. Two counter rotating rotors on a single mast to cancel the torque. In the previous example, we have seen that when the blade is rotating in this direction, the torque is being produced in this direction, which is opposite. This is the torque which is produced. To balance this torque, we have a tail rotor, which is on the tail boom. But in this case, we have a rotor here and a rotor here, which is on a same vertical column. There are two rotors. One will be moving in this direction and the other will be moving in this direction. One will be in clockwise direction, other will be moving in counterclockwise direction, and thus the torque is being balanced over there and it will not destabilize. Tandem rotor configuration. Two large rotors mounted fore and after, that is one at the front and one at the behind. There are two rotors. It utilizes two large lifting rotors mounted one behind the other, allowing for a large CG range and high load capacity. One example for this kind of configuration is Chinook helicopter. That is an example for this tandem rotor configuration. This is rotating in this direction, this will rotate in this direction, it will balance the torque and there is no destabilizing because of this two opposite moving rotor blades. Quadcopter, it is a 4 independent electric motors with fixed pitch propellers, highly popular for small scale unmanned aerial systems. This is the top view of a quadcopter and this is the side view of the quadcopter. multi-rotors. These utilizes 4 or more electric motors with fixed pitch propellers. Their mechanical simplicity and the advent of high energy batteries have made them the most popular configuration for small scale unmanned aerial vehicles. These are the examples of multi-rotor drone types. Tricopter, they have 3 rotors. Then we have 4 rotors. This is quadcopter. 5 rotors, we call it as pentacopter. 6 we have hexacopter. Then we have 7 rotors, 8 rotors, septacopter, octacopter, decacopter. So it goes on. So there is a term, if there are more than 2 rotors, we call it as multi-rotors. And these are the examples for that. Anatomy of a single main rotor unmanned aerial vehicle. The primary components which include in single main rotor design is, it includes the main rotor system, which is here. This is the main rotor system. Then fuselage, this is the fuselage. Tail boom, this is tail boom. And this is a tail rotor to counter the torque which is formed due to the main rotor blade rotation. Functionality, the main rotor provides the majority of lift and directional control, while the tail rotor manages heading and torque. Heading, the direction is being controlled using tail rotor in this case. Mechanical complexity. Single main rotor design requires complex swash plate mechanisms to manage collective and cyclic pitch changes. Aerodynamics of rotorcrafts. It is a simple principle of momentum theory. A rotor acts as a momentum generator, accelerating a mass of air downwards to create an upward reaction force. So, like air from, if we take this as an example, a rotor, so it will take collect the air from all directions, and then it will move it down, it will push it down the propeller so that it accelerates in upward direction. Induced velocity. In hover, the rotor pulls air from above, creating a downward velocity at the disc. This is also called as disc, this part. Right. So normally in many references we'll see that this is the disc, which is nothing but the rotor blades, and this is upward air and this is downward air, downwash. Because of the thrust equation, thrust is equal to the mass flow rate multiplied by the change in velocity of the air. Mass flow rate multiplied by the change in velocity of the air, that is T equals to m dot delta V, that is m dot delta V. Disc loading, the ratio of aircraft weight to the area of the rotor disc. This is disc loading, ratio of aircraft weight to the area of the rotor disc. Hover efficiency. Lower disc loading leads to higher efficiency, thus larger rotor diameters are preferred for long endurance hover missions. Power loading, it is W by P, a dominant design parameter determining hover, climb and speed capabilities. The torque problem and anti-torque mechanics. Torque reaction. Applying power to rotate the main rotor creates an equal and opposite torque that attempts to spin the fuselage. The tail rotor produces side thrust to balance this main rotor torque. This configuration makes the aircraft aerodynamically asymmetric in all planes, requiring sophisticated autopilot algorithms. Blade element theory. Blade element theory analyzes the forces on the rotor by looking at individual infinitesimal sections of the blade. Each section sees a tangential velocity due to rotation and a perpendicular velocity due to inflow. Total rotor thrust and torque are found by integrating the sectional lift and drag forces from the root to the tip. Here in this image, the vectors show the resultant airflow, velocity, the pitch angle denoted by theta, this is pitch angle, and the resulting lift, drag vectors. The inflow angle phi determines the effective angle of attack, which is alpha equals to theta minus phi. Asymmetric flow. In forward flight, the rotor disc experiences a non-uniform velocity field. Advancing blade moves with the flight direction, relative airspeed, that is v rotation plus v flight. Retreating blade moves against the flight direction, relative airspeed is v rotation minus v flight. Articulated rotor, it features hinges for flapping, lead lag and pitch changes. Teetering rotor, which is common in two-bladed rotors where blades flap as a single unit. But here you can see the direction, the flapping, it will move up and down, and this is the lag. When it is moving in this direction, it is lag, and if it is moving in upside down, then it is flapping. Hingeless rotors uses composite material flexibility instead of mechanical hinges to allow flapping, which reduces maintenance but increasing design complexity. The total power, sum of induced power, profile power and parasite power is total power. Induced power is to generate lift, profile power is to turn blades through the air, and parasite power is to the drag of the fuselage. Trend, the induced power decreases with forward speed while parasite drag increases with the cube of velocity. Optimal speed, most helicopters have an optimal bucket speed for maximum endurance. Blade airfoil section, pitching moments. High performance rotor blades often use airfoils with low pitching moments to reduce torsional loads. Thickness, thinner sections are used at the tips to delay compressibility effects as tip speeds approach to Mach 1. Camber, it's symmetrically shaped or slightly cambered airfoils are standard. Scale effects in small rotary unmanned aerial vehicles. Reynolds number, denoted as NR in this case. Small unmanned aerial vehicle rotors operate at low Reynolds number where viscous forces are more significant, and lower Reynolds number results in increased drag coefficients and lower maximum lift coefficients compared to manned helicopters. Small rotors benefit from square cube loss, allowing for lightweight material fractions. Stability and control derivatives of rotary unmanned aerial vehicles. Control is achieved by changing the magnitude and direction of the rotor thrust vector. The longitudinal derivative and lateral stability depend on the rotor's response to angular rates and gusts. Cross coupling. Rotary-wing aircraft exhibit strong coupling between pitch, roll and yaw, unlike fixed-wing aircraft. The effect of ground forces or ground effect, and increase in rotor efficiency when hovering within one rotor diameter of the ground. The proximity of the surface restricts the downwash and reduces induced velocity, requiring less power to maintain lift. It allows heavily loaded unmanned aerial vehicles to take off in conditions where they could not otherwise hover in free air. The auto rotation, which is a safety maneuver, it is a state of flight where the rotor turns due to upward airflow during a descent rather than engine power. It is inspired by the spinning of samara seeds falling from the trees. It provides a means of controlled landing following an engine failure by using potential energy to maintain rotor RPM. Conclusion: Rotary-Wing unmanned aerial vehicles are unmanned aerial vehicles that use rotating wings to generate lift, propulsion, and control. Their key capability is vertical takeoff and landing and stationary hover, making them ideal for missions in confined spaces, shipboard operations, and precise surveillance. Configuration and design: major configurations include single main rotor, which is conventional design with a tail rotor for torque control. The second one is coaxial rotor, where two counter rotating rotors, one on one must. Then we have tandem rotor, where two large rotors mounted fore and aft. Quadcopter, four motors with fixed pitch propellers, popular for small scale unmanned aerial vehicles. SMR designs, single main rotor designs, are mechanically complex, requiring swash plate mechanisms for control, while multi-rotors like quadcopters use differential motor speeds. The aerodynamics and performance of rotor unmanned aerial vehicles. Momentum theory, which explains how rotors generate thrust by accelerating air downwards. Disk loading, it lowers the disk loading and increases hover efficiency. Blade element theory, it analyzes forces on rotor blades by integrating lift and drag along their length. Forward flight creates asymmetric airflow addressed by blade flapping to balance lift. Power requirements: total power includes induced, profile, and parasite components with an optimal speed of endurance. The key challenges and solutions: torque counteracted by a tail rotor in single main rotor or counter rotating rotors which are used in coaxial or tandem configurations. Stability and control: there is a strong cross coupling between axes which requires sophisticated autopilots. Then scaling effects, where small unmanned aerial vehicles face reduced aerodynamic efficiency at low Reynolds number. Safety: auto rotation allows controlled landing after engine failure by using upward airflow. The additional considerations for unmanned aerial vehicle rotary class: we have rotor hub types which include articulated, teetering and hingeless designs, balancing complexity and maintenance. When it comes to airfoil selection, it focuses on low pitching moments and delayed compressibility at the tips. For ground effect, it increases efficiency when hovering near the ground, aiding takeoff. In summary, rotary-wing unmanned aerial vehicles offer unique vertical takeoff, landing and hover capabilities enabled by diverse configurations and complex aerodynamic principles. Their design involves balancing efficiency, control and scale effects to meet mission requirements in restricted environments. These are the references used in this lecture. Thank you.